This course will cover fan controllers for thermal management. In this course, we will start by going through a high-level overview of thermal management. After this, we will delve into details of fan controllers, an important part of thermal management. Lastly, we will introduce signal conditioner products for non-IC temperature sensors. Thermal management in electronic systems is done for one or more of three purposes. Control. Temperature data is an input to a large number of control systems. The control system may be as simple as an on-off thermostatic controller for room temperature, which activates a heater whenever the temperature drops below a specific threshold. Or it may be a complex fan speed control system that uses measured temperature to adjust the speeds of several fans to ensure adequate cooling of system components, while changing fan speeds in such a way as to minimize the audibility of the changes. Calibration. Temperature data is used to correct temperature-dependent errors in a component. Calibration functions can be implemented simply using an analog temperature sensor with an operational amplifier circuit, or they can be much more complex, with a lookup table that provides a 12-bit correction factor every 5 degrees C for a data acquisition system. For example, a TCXO uses temperature to adjust the operating parameters of a crystal oscillator to compensate for the shift in the crystal's resonant frequency over temperature. Signal conditioners for sensors, such as pressure transducers, use temperature data to correct thermally induced drift in the transducer's characteristics. Protection. Many components in electronic systems can be exposed to temperature extremes that can damage them. This can range from ambient conditions, power dissipation in nearby components, or their own power dissipation. Thermal management components can be deployed to detect, and in some cases eliminate, potentially dangerous thermal conditions before they can cause damage. Again, these solutions can be as simple as an over-under temperature detector to protect circuit board components from damage, or as complex as a cooling system that uses temperature data from multiple locations to ensure proper operating temperature under a variety of external conditions. Fans are used in electronic systems that require airflow to provide sufficient cooling for the various components. If you use a fan, or multiple fans, that can move enough air to sufficiently cool the system components under worst-case conditions, such as maximum ambient temperature or maximum power dissipation, that fan will keep the internal temperatures low enough to avoid component damage. However, the system will not normally be operating under worst-case conditions. In fact, the amount of time a system spends at or near the worst-case thermal conditions is often a small fraction of the system's operating life. Therefore, constantly running the fan at its nominal or full speed is not necessary. Sometimes no cooling is necessary. At other times, limited cooling is sufficient. In addition to being unnecessary, continuous full-speed cooling has disadvantages. These include unnecessarily high acoustic noise. Fans are noisy. Multiple fans are noisier still. The noise level increases with speed, so if the fan is operated at its full nominal speed continuously, the noise level will be higher than it needs to be. At a minimum, the excessive noise is unpleasant for people working nearby. At higher sound pressure levels, excessive fan noise can damage the hearing of those nearby. Therefore, any equipment that includes cooling fans and is operated in the presence of users should employ some method of reducing fan speed when full cooling is not needed. Reducing the annoyance level of fan noise can improve marketability of equipment. In some cases, maximum noise levels are mandated by legislation, effectively requiring some form of fan control. Wasted power. Fan power dissipation varies dramatically, from small fractional watt fans used in compact equipment to large fans that require well over 100 watts of input power. A fan spinning at full speed when that speed is not needed is wasting power, increasing operating costs, and adding to the equipment's carbon footprint. Reducing fan speed when less cooling is needed can reduce the power waste, resulting in lower costs and lower overall carbon dioxide emissions. Reduced fan lifetime. Since the operating lifetime of a fan is related to the total number of revolutions, running the fan at less than full speed can increase the fan's operating life. If the fan's average speed can be cut in half, the fan's lifetime can be roughly doubled, which improves reliability and reduces maintenance costs. The function set of a fan control circuit includes control of fan speed, accomplished either by adjusting the fan's power supply voltage or by generating a PWM signal whose duty cycle controls the speed of the fan. Monitoring of fan speed is normally done by monitoring the fan's tachometer or tach output. This method utilizes an output that produces a specific number of pulses per revolution. Sometimes this is done by monitoring the fan's supply current, although this is much less reliable. Detecting fan failure is usually done as part of the fan speed monitoring process. It can also be done by fans that have fail or locked rotor outputs instead of tach outputs. Monitoring the speed of a fan when driven to its full speed also allows predictive fan failure detection. As fans near end of life, they can begin to slow down. By detecting this phenomenon, a system can ensure that a fan near the end of its useful lifetime is replaced before failing completely. Closed-loop control of fan speed is a combination of fan speed control and monitoring. By monitoring the fan's tachometer signal, the speed of the fan can be adjusted to force it to a desired value. Ensuring low audibility of speed control means adjusting the speed of the fan to match the system's cooling requirements. That can help to reduce the average noise level produced by the fan. However, it is necessary to be aware that each time the fan's speed is changed, the change in noise level can be very apparent to anyone near the system. The best fan control ICs include features that help to reduce the audibility of fan speed changes. Monitoring of temperature. The fan controller can include one or more channels of temperature sensing. Temperature-based fan speed control. Temperature data can be used to adjust fan speed based on system-specific temperature speed profiles. The best way to control the speed of a fan depends on the type of fan. Brushless DC fans are the most common type used to cool electronic equipment. These fans are available with power supply voltages of 5 volts, 12 volts, 24 volts, and 48 volts. 12-volt fans are the most common. 5-volt fans are often found in portable equipment, such as notebook PCs. 48-volt fans are commonly used in industrial and telecommunications equipment. There are 3 categories of brushless DC fans, referred to by the number of wires on the fan, as shown on this slide. The simplest is the 2-wire fan, which just has power supply connections. A 3-wire fan also has power supply connections, plus an additional wire that provides information about the fan's status. There are 2 standard functions for the 3rd wire. This 3rd wire may be a tach output or a locked rotor output. A tach output is usually an open drain logic output that produces a series of pulses as the fan spins. Most fans produce 2 pulses per revolution, but fans producing 1, 4, or 8 pulses per revolution are also available. By determining the period or frequency of the tachometer pulses, the fan's speed can be calculated. This data can then be used for closed-loop control of the fan's RPM by comparing the actual RPM with the target RPM and then adjusting the drive to the fan until the actual RPM matches the target RPM. The tachometer signal can also be used to detect fan failure. For example, if a fan's speed is calculated to be 300 RPM under full drive conditions, but its nominal speed is 4,000 RPM, it can be safely assumed that the fan has failed. Another use for the tach output is to detect incipient fan failure. Prior to failing, many fans will spin more slowly at a given drive level than they did when new. By monitoring the fan's speed versus drive profile, it is possible to determine that the fan is beginning to slow, thereby allowing the fan to be replaced before it has completely failed. This improves system reliability by preventing fan failures and also reduces maintenance costs because emergency fan replacements and potential system damage become less likely. The other common 3-wire function is a fan failure or locked rotor output that indicates that the fan has stopped spinning. While less flexible than a tach output, the locked rotor signal gives an unambiguous indication of fan failure or obstruction. 4-wire fans add a PWM speed control input. By varying the duty cycle of the PWM waveform supplied to this input, the speed of the fan can be varied over a range of about 30% to 100% of the maximum speed. The recommended PWM frequency is in the range of 15 kHz to 30 kHz for most fans, although some fans will accept input frequencies as low as 100 Hz or as high as 100 kHz. The logic levels are usually compatible with 3.3 volt or 5 volt logic. It is clear that basic speed control is easy to do with a 4-wire fan. A microcontroller can generate a PWM waveform, as can most fan speed controller ICs. However, 4-wire fans are still less common than 2- and 3-wire units. In some cases, the right fan for the application is available only as a 2- or 3-wire unit. Controlling the speed of a 2-wire or 3-wire fan can be somewhat more involved, because these fans do not have a dedicated speed control input. Instead, the speed of these fans must be controlled by modifying the supply voltage applied to the fans. If you vary a fan's power supply voltage, the fan speed will vary. This figure shows fan RPM versus fan power supply voltage for a typical low-cost 12-volt fan. The fan speed in this example is roughly proportional to the supply voltage. One way to vary the fan's power supply voltage is shown here. The low dropout voltage regulator, LDO, provides power to the fan. The digital to analog converter, DAC, controls the LDO's output voltage by driving its adjust input. This approach allows a microcontroller to vary the fan speed by writing control data to the DAC. Some dedicated fan control ICs implement a similar approach by integrating the DAC and LDO functions along with other features. A lower cost, more efficient approach is to modulate the fan's power supply with a PWM waveform. The power supply effectively turns on and off at a rate of roughly 30 Hz. Because the pass transistor is always either fully on or fully off, its power dissipation is negligible compared to the power used by the fan. The most obvious approach to monitoring fan speed is to count the number of tachometer pulses occurring during a fixed period of time, as shown in Figure A. This works well if it is possible to count a suitably large number of pulses during a sufficiently short period of time. As an example, a 3000 RPM fan that produces 2 pulses per revolution will generate a 100 Hz tachometer signal when operated at full speed. If we need to measure and update fan speed once per second, we will be able to count only 50 pulses when the fan is spinning at half speed. This may give enough resolution to determine that the fan is operating, but not enough for precision fan speed control. The most widely used approach is for the fan controller to generate a reference clock, generally in the range of a few kilohertz, and count the number of clock cycles that occur during a fixed number of tachometer periods, usually 1, 2, or 4, as shown in Figure B. This allows a tachometer count to be completed in a few milliseconds, so the approach is compatible with closed-loop fan speed control. In many cases, fan speed control is really fan drive control. For a given thermal condition, you provide the fan with a corresponding PWM duty cycle or supply voltage. The actual fan speed may vary from the nominal value by several percent due to fan-to-fan variations, power supply tolerance, and other uncertainties. This open-loop speed control is sufficiently precise in many systems. In other cases, especially when acoustic noise levels or supply current are important, you may prefer to have control over the fan's actual RPM. When you can accurately monitor the tachometer, it becomes possible to control the fan's RPM by adjusting the drive level to produce the desired tachometer frequency, or period. Fan speed accuracy as good as plus or minus 1% can be achieved, depending on measurement resolution and clock accuracy. Closed-loop fan speed control is available in several of Maxim's fan controllers. Most fan controllers that have temperature sensing capability are also able to control fan speed based on the measured temperature. The details can vary. Most such fan controllers use some sort of straight-line mapping between temperature and fan drive, while others have a lookup table that associates a few temperature values with fan drive levels. Still others map temperatures to fan RPM values. There are several different ways to implement fan control in a system. The best approach for a given system depends on the characteristics of the system, the ease or difficulty of developing new fan control firmware, and other factors. Some common approaches are shown here. We'll look at them each in the next few slides. If the system design already includes a microcontroller performing system management tasks, that microcontroller may also be able to handle fan speed control functions. The microcontroller needs to have enough IOs available to monitor tach signals and generate PWM speed control signals. If the system microcontroller doesn't have the bandwidth or I/O capacity for managing the fans, consider using a dedicated fan management or system management microcontroller. Fan management microcontrollers include a sufficient number of I/Os to monitor tach signals and generate PWM control signals for multiple fans. They also have sufficient command flexibility and memory space to handle a variety of complex fan management algorithms. In addition, they include temperature monitoring capability. System management microcontrollers also include facilities for monitoring, sequencing, and margining power supplies. In some cases, the system management microcontroller will also include black box recorder style fault logging in non-volatile memory for root cause analysis and design improvement. When a system management microcontroller is capable of monitoring temperature and determining target fan speeds, but does not have enough IOs or bandwidth for controlling and monitoring the speeds of multiple fans, or if the time and cost involved in developing intelligent fan control firmware are excessive. The fan speed control IC need not include temperature sensing capability. In this approach, the system microcontroller monitors temperature and selects the target fan speeds. The fan control IC provides the fan IOs, ramp rate control, fan monitoring and error detection, and RPM control, reducing the I/O and firmware load on the microcontroller. In many cases, it is best to offload the fan control functions from the system microcontroller. To do this, use a fan speed control IC with integrated temperature sensing. This approach provides a simple fan speed control algorithm, generally with the control parameters selected by the system microcontroller, and relieves the system microcontroller from having to monitor temperature and make speed decisions in real time. This approach can simplify the system and reduce costs by integrating the sensing and speed control functions. A standalone fan controller requires no microcontroller to set up the control algorithm. Instead, the control characteristics are selected externally, for example by using resistors and capacitors or by strapping pins. Signal conditioners for non-IC temperature sensors work with thermistors, RTDs, or thermocouples to help interface those sensors to systems. This slide shows a simple circuit for thermistor conversion. The MAX 6682 has an input for a single thermistor and a voltage reference output to drive the thermistor-resistor voltage divider. The digital data is serial and read-only. As with the MAX 6698, the datasheet includes a table showing how the output code maps to thermistor temperature for a common thermistor type. The MAX 31865 is a monolithic solution providing signal conditioning, measurement, input protection, and fault detection for RTDs. It supports RTDs ranging from PT100 through PT1000 in 2, 3, or 4-wire configurations. 3-wire measurements require no matched current sinks and are therefore more accurate than typical ADC solutions. The equivalent temperature measurement over the full temperature range is well under plus or minus 0.5 degrees C. It offers plus or minus 45 volts of input protection against overvoltage conditions on the RTD or cable. In addition, the MAX 31865 performs checks on each of the 4 RTD terminals, so it can detect and report virtually any short or open of any of the RTD wires. Signal conditioning for a thermocouple consists of a local temperature sensor, precision amplifier, ADC, and voltage reference. Maxim has developed several ICs that integrate all of these functions, converting thermocouple output voltages into digital values, adding the cold junction temperature to the result, and producing the output data in degrees C, using a straight line approximation for the thermocouple curve. Both the cold junction compensated data and the cold junction temperature value are available if linearization calculations are desired. The MAX 31856 is a highly integrated IC that digitizes the signal from any of the most popular type of thermocouples, reporting an output formatted in degrees Celsius. This converter resolves temperature to 0.0078125 degrees C and allows readings as high as plus 1800 degrees C and as low as minus 210 degrees C, depending on the thermocouple type. With use of its onboard temperature sensor or with user-supplied temperature data, the MAX 31856 automatically performs cold junction compensation and linearization correction, which greatly increases the accuracy with few to no required external components or system software. The thermocouple inputs are protected against overvoltage conditions up to plus or minus 45 volts. A lookup table stores linearity correction data for several types of thermocouples, including K, J, N, R, S, T, E, and B. Line frequency filtering of 50 Hz and 60 Hz is included, as is thermocouple fault detection. An SPI-compatible interface allows selection of thermocouple type and setup of the conversion and fault detection processes. Applications for the MAX 31856 are wide and varied and include, but are not limited to, such industrial equipment as temperature controllers, industrial ovens, furnaces, environmental chambers, plastic injection molding equipment, and fuel cells. Evaluation of the MAX 31856 is supported with the MAX 31856 EV kit.
To summarize, in this course, we gave an overview of thermal management, details of fan controllers, and introduced signal conditioner products for non-IC temperature sensors. For more information on this topic, please go to our website at www.maximintegrated.com under Products, Sensors, and Temperature Sensors. We hope you enjoy this video and see you again in another educational video of Maxim Integrated.